What specific problem does program trace prompting, PTP, aim to solve in the context of chain of thought prompting, and why is this problem significant?
Program trace prompting, PTP, aims to address the issue of unfaithful outputs in standard chain of thought, COT prompting, where explanations can be incorrect yet superficially plausible, failing to align with sequential causal reasoning. This problem is significant because unfaithful explanations undermine the utility of COT for justifying responses to end users and complicate the analysis of reasoning processes. PTP introduces a semi-formal syntax that structures COT explanations into identifiable steps, allowing for easier analysis and evaluation of the reasoning involved. By ensuring that each step is modular and well-defined, PTP enhances the ability to detect and measure errors, thereby improving the reliability of the reasoning process. Ultimately, this structured approach not only preserves the flexibility of COT, but also enhances its applicability across diverse tasks while facilitating deeper insights into the model's reasoning capabilities.
Can you describe step by step how the PTP method operates, including how it differs from standard chain of thought prompting?
The program trace prompting, PTP method operates by wrapping few-shot chain of thought, COT, demonstrations in a semi-formal syntax that clearly identifies and names each reasoning step, defines their input-output behavior, and replaces COT explanations with structured traces of these steps. Specifically, it uses Python-like pseudocode to represent each step, allowing the LLM to generate a new trace for a novel input based on the provided structured context. Unlike standard COT prompting, which can produce unfaithful and syntactically diverse outputs, PTP ensures that the generated traces are well-formed and can be automatically parsed into legal sequences of defined steps, with over 99% of steps being syntactically correct. Additionally, PTP allows for the execution of individual steps, enabling a form of interactive debugging, which is not possible with traditional COT prompting. Overall, PTP enhances the analyzability of reasoning processes by making the steps explicit and modular, facilitating the identification of errors and improving the overall reliability of the outputs.
Provide a detailed example using a specific task from your experiments that illustrates how the PTP algorithm generates traces. What inputs and outputs are involved in this example?
In our experiments, we applied the program trace prompting PTP algorithm to the task of sports understanding, specifically using the input, Drew Brees went for it on 4th down. The PTP process begins by replacing the input in the prompt with a specific function call, such as _sport_for Drew Brees . This function is designed to return the sport associated with the athlete Drew Brees. The PTP algorithm generates a trace that includes a sequence of function calls, such as _analyze_input_, followed by _sport_for , and potentially other subroutines like _consistent_sports . The output of this trace is the final answer produced by the last function call, which in this case would be the sport associated with Drew Brees, typically football. This example illustrates how PTP structures the reasoning process into modular steps, allowing for clear input-output relationships and facilitating error analysis.
What are the advantages of using PTP over traditional COT prompts, particularly in terms of error analysis and modularity of steps?
Program trace prompting PTP offers several advantages over traditional chain of thought COT prompts, particularly in error analysis and modularity of steps. Firstly, PTP allows for detailed analysis of the reasoning steps involved in a COT explanation, enabling the identification of local errors specific to individual steps, as well as non-local errors that arise from incorrect algorithmic sequencing. This modularity is defined such that each step's behavior depends solely on its labeled inputs, making it easier to evaluate and characterize errors. Experimental results indicate that most steps in PTP are modular, facilitating a clearer understanding of where errors occur, which is not possible with conventional COT explanations. Additionally, PTP outputs can be automatically parsed into well-formed sequences, ensuring that over 99% of steps are syntactically correct, thus enhancing the reliability of the reasoning process compared to the often ambiguous outputs of standard COT prompts.
How did you validate the effectiveness of the PTP method, and what metrics or benchmarks did you use to measure its performance against regular COT prompting?
The effectiveness of the program trace prompting (PTP) method was validated by implementing it across 23 diverse tasks in the Big Bench Hard (BBH) benchmark, comparing its accuracy to that of standard chain of thought (COT) prompting. The results indicated that PTP maintained comparable accuracy to COT prompts, with only one task showing a statistically significant loss in performance, while 3 tasks demonstrated significant improvements. Additionally, the PTP outputs were analyzed for syntactic correctness, revealing that over 99% of the steps were well-formed and more than 95% of function calls were syntactically correct Python objects. The paper also introduced metrics such as call correctness, syntactic correctness, and type correctness to evaluate the generated traces, confirming that PTP traces could be automatically parsed into legal sequences of defined steps. Overall, the analysis showed that PTP not only preserved performance, but also allowed for deeper insights into the modularity and locality of errors in reasoning, which are not easily assessed with traditional COT methods.
What limitations or potential drawbacks did you identify in the PTP approach, and how might these impact its practical applications?
The program trace prompting (PTP) approach has several limitations that could impact its practical applications. Firstly, while PTP aims to produce structured explanations, it still faces challenges with overgeneration, where the LLM may continue generating steps beyond the requested one, complicating trace accuracy. Additionally, the performance of single-step prompts is more variable compared to full PTP prompts, indicating that isolating individual steps may not yield consistent results. Furthermore, the presence of non-local errors, which arise from the LLM guessing the wrong algorithm from the few-shot program traces, suggests that even if local steps are correct, the final output may still be incorrect. Lastly, the assumption of stable incremental generation, which underpins the measurement of modularity, may not always hold true, leading to potential inaccuracies in evaluating the modularity of steps. These limitations could hinder the reliability and interpretability of PTP in real-world applications.